Now here we could see the final structure of benzene. The actual structure of benzene is a planar regular hexagon. This is the planar structure. This is the cyclic structure. This is called as closed ring structure as a regular hexagon. You can see the same structure here, only here we have shown the bonds. Here we have shown the carbon with the hydrogen along with some dotted structure in the cyclic ring. Bond angle is 120. Now here you can see the bond angle which is around carbon atom is exactly 120. So for every carbon atom, if you check, the bond angle around that carbon atom is equal and same, that is 120 degrees Celsius. Sorry, 120 degree. The ring represents the delocalized electrons within the benzene molecule. Now what do you mean by this delocalized electrons? We can see these electrons which can be moved. These pi electrons which can be moved. These are called as delocalized electron. If you can see this carbon-hydrogen bond, it also contains some electrons which are getting involved for sharing the bond. But these are called as localized electrons. Also, this carbon-to-carbon bond, these are also sigma bonds. Every carbon atom, it is attached with the next carbon atom with the sigma bond, and these CH bonds, these are also sigma bonds. So all these sigma bonds contain electrons, but these are called as localized electron, which are fixed on that position. If you can see this dotted structure, whenever we say that this benzene structure contains alternate single and double bond. So all these double bonds, those are attached or those are containing certain pi bonds. So these pi bonds we are showing like this with the help of dotted line. These are called as delocalized because we are saying or we are stating this statement because there are two different resonating structures for benzene that we have already seen. So either you can draw this structure or you can draw this structure. So you can say these pi bonds are moving in nature. Hence these are called as delocalized electrons. So the ring represents the delocalized electrons within the benzene molecule. Next, representation of pi cloud in benzene. So each carbon atom has an electron in a pi orbital. So this is the general structure of representation of pi cloud. So in detail of this structure, how we can draw this structure and what are these orbitals, that I will explain in the next slide. These pi orbitals overlap forming pi bonds. So these all pi orbitals of every carbon atom overlap with each other at the top position of this carbon to carbon sigma bonds and at the bottom position of the carbon to carbon sigma bond. So this is termed as pi cloud of the benzene ring. The electrons in the pi bonds become delocalized, leading to a pi electron cloud above and below the ring. So this is the pi cloud which is present due to pi bonds, due to pi electrons which are present in the benzene structure. Now next we can see bond order. What do you mean by bond order? The definition is, it has the formula, that is total number of bonds divided by total number of resonating structures. So you can see what do you mean by total number of bonds. For that we will see. Now see, this is the molecular formula of benzene, C6H6. Now if we show the Kekel structure, two different resonating forms, you can see here, if you consider only this carbon and this carbon, so total number of bonds, again you have to consider, for calculating bond order, you have to consider these two structures at a single time. So from these two structures, if you see, if we are considering this first carbon and this second carbon. Here also it is first carbon and here it is a second carbon. Okay, wait. Suppose this is the first carbon, this is the second carbon, and also from this second resonating structure, if we consider these two carbon atoms. Now we have to see total number of bonds. So the total number of bonds present are, this is 1, 2, 3. So from these two structures, if you consider it simultaneously, we have to consider these two structures for calculating bond order. So the total number of bonds which contains between these two carbon atoms are 3 divided by total number of resonating structures. So how many resonating structures are possible for benzene? They are 2. So 3 divided by 2, it is 1.5. What this bond order indicates now? Now this bond order, it means what do you mean by bond order? Now the value we are getting, it is 1.5. Means what? Whenever you draw the structure of benzene here, if you draw the structure of benzene, here you are drawing this dotted line. Or we will move on to our previous slide. Now see, here it is a single bond along with this dotted bond. Means what? This is one complete bond which is fixed, and this is partial bond that we have drawn. So it is considered as 1.5. So this is indicating the bond order of these two carbon atoms. Similar way, if we go for all the next carbon atoms, you have to consider two carbon atoms at a time for two resonating structures of benzene. So every time you are getting this bond order as value is 1.5 for all the benzene structures. Hence we are drawing this structure as like cyclic structure of carbon to carbon sigma bonds, and in that closed cycle we are drawing this dotted line. So it is representing a 1.5 bond order for every two carbon atoms. Hence you can draw this type of structure. This is the significance of bond order which are getting the value as 1.5. Now next we will move on to C6H6. We know the carbon atom is having electronic configuration as 1s2, 2s2, 2p2. So everyone of knows this carbon atomic number, it is 6. So we are representing this as 2s, 2p. 1s will be fixed where you are showing two electrons, two paired electrons in the 1s orbital, right? Next you have 2s2 and 2p2. So this is your 2s orbital, this is 2p orbital. So for 2s, these two electrons are fixed, which are paired in nature. Next, for 2p, there are 2p2. So we are filling first 2px and 2py. 2pz is the blank one. This is the case in the ground state. So but in the case of excited state, one electron from 2s orbital is promoted to 2pz, and we are getting the structure as 2s, one electron, 2px, one electron, 2py, one electron, and 2pz, one electron. So one electron is present in every 2s and 2p orbitals. So whenever we go for its hybridization for generating a structure of benzene, this sp2 is getting involved. So this is sp2 orbital, Here we can see this is sp2 hybridization for benzene, as it is an C double bond C. As all of us know, if we consider CH4, that is methane molecule, it is sp3 hybridization. For C double bond C, it is sp2 hybridization, and for C triple bond C, it is sp hybridization. That all of us knows this three types of hybridization which carbon can undergo. So for benzene, that is which contains C double bond C molecule, C double bond C atom, it contains sp2 hybridization. Next, if we consider, now these are the different resonating structures which are involved. So how to draw these structures? You know, this benzene molecule you can draw. This bond can shift over here, this can shift over here, and this can shift over here, which you can give second resonating structure. Now here you can see I have drawn a benzene ring with, I have shown the every carbon atom is bonded to a single hydrogen atom, and every carbon is sp2 hybridized carbon. So from where this sp2 came? This sp2 came from this carbon to carbon single bond. This is again a single bond, and this is one hydrogen atom which is attached on every carbon atom. Here it is also one hydrogen atom which is attached. So if we want to see the structure of this, you can see here C double bond C with two hydrogen atoms. Now you know this type of structure, that is called as sp2 hybridization. This is first carbon, this is second carbon. Now we will go in detail of every bond. Now see, this is 2pz orbital. As we have seen in the last slide, the electronic configuration of carbon atom, the 2pz orbital which is getting filled in the excited state after promotion of one electron from 2s orbital. So this 2pz orbital of every carbon atom from the benzene structure will contain single electron. Okay, next, this carbon atom, it is bonded to second carbon atom with the help of sp2 orbital which is containing sigma bond. So this every carbon atom of this are bonded to each other with the sigma bond. Next, hydrogen atom which is attached with the carbon atom with the help of again sigma bond. So this is called as sp2s overlap. So this carbon is of sp2, hydrogen will be the s orbital of hydrogen is going to overlap with the sp2 carbon, sp2 orbital of the carbon. So this is called as sp2s overlap. Okay, again this carbon is getting overlap with the next hydrogen atom of the sp2 of the s orbital of the hydrogen. So again here it will be a sp2s orbital overlap. So this we can say which is occurring in every alkene structure or every carbon to carbon double bond structure. Now next, the p orbitals of every carbon atom which is getting filled with the one electron in the excited state. Now these electrons from the p orbitals are overlapping with each other, forming a pi bond. Now this is called as pi cloud, which is present above and below of the sigma bond. You are getting this. This is called as pi cloud, and which is getting formed by the pi bond of the electrons. That is, pi electrons are forming a pi bond. Next we can see this is called as sigma frame. Now what do you mean by sigma frame? Here you are showing every carbon to carbon bond structure. Now see, for this, if you see, if you can consider this carbon atom, suppose this is your this carbon atom. This carbon is bonded to one hydrogen. It is bonded to one hydrogen, so it is an sp2s overlap. Next, this carbon is bonded with the second carbon atom. So this is your second carbon atom. These two carbon atoms are bonded with each other with the help of sp2 overlap, like this similar way we are talking. So this is an sp2 overlap. Now this is our second carbon atom which is bonded to hydrogen. So it is again sp2s overlap. So see here, it is an sp2s overlap. Next, this carbon atom which is bonded to next carbon atom again with the sp2 bond. So this is again sp2 bond for this carbon atom. Like this way, every carbon atom is bonded to next carbon atom with the help of sp2 overlap. So all these are sigma bonds, hence it is called as sigma frame structure. And every carbon atom is overlapping with the s orbital of hydrogen, which can be shown by sp2s overlap. So this is the sigma frame of benzene structure that we can see. This is the front view and this is side view of this p orbitals. Here now you can see the p orbitals which are standing over here like this of the carbon atom which are forming a pi bond, that you can see over here, which are standing. Suppose this is your horizontal plane and this p orbital as it is present vertically. So you can see here the pi orbitals which are sharing pi electron along with each other to form a pi cloud.